Yes. All right, we're going to get started. Good morning, everyone. Welcome to the full paper session on flow topology and uncertainty. Our first speaker today is Tobias, and he's going to talk about objective Lagrangian vortex cores and their visual representations. Please go ahead.
All right, great. Thank you so much for the kind introduction. Hello, everyone. I'm Tobias Günther, and this is work together with Holger Theisel. And I'm very happy to tell you about our work about the objective extraction of vortex core lines, which are guaranteed to be path lines of the fluid flow. So this work is about vortices, and vortices can be found pretty much everywhere. We have them, for example, in the wake of airplanes, in the oceans, where they carry entire ecosystems around, or in atmospheric flows, such as in the wake of volcanic islands. In flow visualization, we usually want to find algorithms that are able to detect vortices, even when there are no clouds or plankton around that would make them visible. Now, in the simplest setting, when the vortex is not moving, we have a pretty clear understanding of what a vortex should look like. We expect a critical point in the middle and closed streamlines around it. That means particles are traveling very nicely on circular paths around. If, however, our vortex now starts to move, then a standing observer would see the vortex pass by. And because of the relative motion between the two, the observer sees all the particles moving sideways. And this apparent motion is now a superposition of the spiraling motion in blue and the movement of the vortex in red, giving us these purple vectors here, which means we no longer see these nice characteristic closed streamlines. Now, if the observer, on the other hand, would move along with the vortex, then there wouldn't be a relative motion between the two. And so the observer truly sees the spiraling motion the whole time. So when we look for such spiraling motions, the question is, how do we figure out what the right observer motion is? Now, this has been theorized for quite a long time. Luke and also later Robinson said decades ago that we should be looking for a reference frame in which the flow becomes steady. That is, the observed flow should be as steady as possible. In 2017, we developed the first objective optimization algorithm that finds this optimal observer motion. And back then, the observer was restricted to rotations and translations, just like this. I will now show you some follow-up work that came later. And to discuss the differences between them, we will compare the methods based on a handful of properties. The first is whether the optimization takes place per time slice or not. If so, then there's no guarantee that the observed motion is temporally consistent. Second, does the downstream feature extraction happen on exact so-called killing fields, or are we potentially interpolating between observers? And lastly, is the vortex core line guaranteed to be a path line or not, which is usually a very common quality criterion when we extract vortex cores. Now, the method has been extended then in several ways. Here we optimized for vortex cores of finite-sized particles, so not just massless particles, so it extended it into higher dimensions. The observer motions that were looked for were extended towards affine transformations, later also towards completely spatially varying transformations by modeling them with Taylor expansions. Neural networks have been trained in a supervised manner, which can increase the robustness to noise. And then came an important step. Hartwiger and colleagues have shown that the objective function of the optimization can be expressed very elegantly using a so-called Lie derivative, which finds the time derivative of a vector field under motion in another vector field. And in addition, they also phrased the first global optimization that looked for observers in all time slices at once. Now, thanks to this Lie derivative, the approach could also be very easily extended to curved spaces. Now, with all the methods above, there might be a different optimal observer at each point in the domain, since multiple vortices might move in different directions. And here, Zhang and colleagues built a tool that explores this zoo of different observers, from which one can be picked for closer inspection, and which also means that all feature extraction then happens in exactly that one selected reference frame. And recently, Rautek and colleagues searched for reference frames and vortex core lines at the same time. So they optimized them together, which included an energy term that tried to make the core lines become path lines. But this is only a soft constraint, and there's therefore no guarantee that this constraint is met. Now, in contrast, in this paper, we present the first approach in which the vortex core lines are guaranteed to be path lines of the flow. And by the way, all these methods here are objective, except for one. Which one is it? It's the neural network, of course, right? Because for neural networks, no promises can be made. Okay, so how does our approach work? Let's say within a certain region, we want to find the observer motion field W, which makes the flow steady. And we want the observer to follow along a path line. Then the characteristic property is that the observer motion must be tangential to the path line, exactly along the path line. This restricts the observer motion to a killing field with a known translation. And so the only unknown in this whole system is the rotation omega of our observer. And note that the unknown rotation omega is linear in this observer motion, which is quite useful. Now, using the Lie derivative, which is expanded here, we can now measure how steady is the observed flow. And again, note that the unsteadiness m here is linear in the observer motion, which in turn was linear in the unknown rotation, which means everything's linear, and this turns it into a nice linear system. We minimize now the squared unsteadiness in the vicinity of the given path line in both space and time, so inside a tube around the path line, which makes this a quadratic variational minimization problem where the time-dependent rotation is our only unknown. And then upon discretization, we can solve for the unknowns by solving a sparse linear system. We call the energy residual VDE, which is short for vortex deviation error, and this is what VDE looks like. It's a scalar field here shown for the Kármán vortex street. Inside each vortex region, there is a distinct minimum of the VDE measure, which we use to define the center of the vortex. It's a slightly more complex example of a flow around a heated cylinder, and we can see that the VDE is nicely temporally stable and very smooth. Algorithmically, the vortex extraction goes as follows. Given a vector field, we first compute a path line for each grid point. And in the vicinity of each path line, we can then solve for the optimal observer rotation, which was the only unknown of the system. This is done per grid point, and to achieve subvoxel accuracy, we refine this with a gradient descent. And then in 2D, the vortex core line is determined simply by a local minimum of VDE. And in 3D, it is determined by a valley line of VDE, which we extract numerically using a recent variational method that we published earlier this year. And lastly, for visualization, we subtract the observer motion from the input vector field and visualize the vortices by showing spiraling streamlines at selected time steps. This is what this looks like in 3D. First, we find the valley line of VDE here shown in blue, and then those can be advected along path surfaces in 3D or path lines in 2D. And after a selected number of time steps, we seed evenly spaced streamlines, which are tapered at the start to convey the rotation direction. And the color here simply encodes the time step. This visualization is devised to work both in 2D and in 3D. For further evaluations, I refer you to the paper where you can find parameter studies, ablations, performance measurements. Just to give you an impression, in 2D, the extraction is the order of a few seconds, and in 3D, it's in the order of a few minutes. So in summary, we propose the first objective vortex core line extraction algorithm with which vortex core lines are guaranteed to be path lines of the flow. The idea was to restrict the observer motion to follow along path lines, and with this, the only degree of freedom is the rotation of the observer, which can be optimized variationally by solving a linear system. And we built the system for 2D and 3D flow data, and a demo implementation can be found online on GitHub. Yeah, thank you very much for your attention. I'm looking forward to your questions.
All right, thank you very much. While folks are typing in questions, I have a first one. It appeared to me that the optimization is happening also per core line. Is that true?
Yes. Yeah. So first we optimize for each grid point the VDE measure, and this only gives you a grid resolution for the location where the grid points might be. They're only sitting for now on the grid locations on the grid, and you can use this as a seed point and do a grading descent to find an accurate solution even between the voxel grid points.
Right. Okay. So while I'm waiting for more Slido questions, a follow-up one is that when you are deriving the path line center for 3D case, I saw those what you define as VDE regions. They do merge. What happens when they merge, and what happens to your path line definitions?
So the regions that you speak of, you probably mean in the VDE scalar field. We're restricting the search for the minima, which is defined through a scalar field called instantaneous vorticity deviation. It's a classic region-based objective measure, and it can happen that vortices come close to each other. Yeah, and that means the regions in which you are looking for vortex centers are overlapping. And when you do the optimization for the observer motion, then the assumption is always that within this little space-time tube around the vortex, there's only one vortex inside. Or at least if there's multiple vortices, then they should move in the same direction. Otherwise, you get kind of a least square compromise between two motions.
So in another word, the optimization still works when you have interactions because you still constrain the optimization to individual element or
when the region over which you do the optimization contains one observer motion, so one vortex. If it's two vortices, they might be moving in different directions. If they move consistently, if they move together, then it's fine. If you have multiple motions and have one optimization over a larger region which covers both, then you get a least square compromise of the two.
Okay. I have a quick question. It says, nice work. Have you tried this on the John Hopkins turbulence flow?
Oh, no, that we haven't tried yet. So the John Hopkins turbulence database has very turbulent settings with extremely high Reynolds numbers. So there is also an interesting challenge that vortices are changing and breaking up. And so you have much more dynamics. That would be the next big step. Yeah.
Okay. All right. Thank you very much. We will move on to the second speaker. Thanks again. All right. For the second speaker, we have Tanner, who is going to talk about localized evaluation for constructing discrete vector field. Please go ahead.
All right, thank you for the introduction. Hi, everyone. I'm a PhD student at the University of Arizona. I'll be presenting this work made with my co-authors, Julien Tierny and Josh Levine. In this work, we've made a new algorithm which takes as input a piecewise linear vector field and outputs a discrete vector field, both of which I will explain later. The reason we would like to change representation is because the discrete field offers certain advantages, like robustness and simplicity when extracting features and simplifying them. The problem is effectively choosing a discrete field that matches the underlying flow. Previous work in this domain, called FastCVT by Reininghaus et al., generated the field by optimizing the flow geometry of the discrete field. They did this by iteratively computing shortest paths along the entire field for reductions. The main drawback of this approach is that it can be slow on larger datasets. In this work, we've learned that you can look locally to generate the field and still generate some similar results. So now, when running the algorithm on a large complex of over 48 million simplices, it only takes a couple of minutes compared to many hours it would take with FastCVT. Here, you can see the discrete critical points extracted by our algorithm and are colored by type. Now, to get into the details. I'm first going to describe what the input looks like and why we would like to change representations. The input is going to be a 2D triangulated mesh where the vectors are defined on every vertex. The vectors typically represent flow and have been used in many domains like physics, biology, and chemistry. To determine flow throughout the space, we use piecewise linear interpolation. The analysis of these fields aims to extract important topological features within the flow, such as critical points and separatrix lines. Critical points are where the vector value is 0. There are 6 critical point types for a 2D vector field. In particular, a saddle is going to be important because you can generate the separatrices by integrating the 4 main directions around a saddle. However, an issue with integrating these streamlines is their non-robustness to noise and numerical imprecision. So an alternative to computing this over a continuous range is to use discrete representations, which store a finite set of objects that replace numeric computations with robust primitives. There are multiple ways to discretize a vector field. I will give a couple examples. A simple option is to look at a piecewise constant vector field, where the vector is stored on each of the higher dimensional cells in the mesh rather than on each vertex. Each cell will have constant flow through it. An example of work analyzing this field is one done by Subone et al. Another option is to discretize based on the regions of flow. Each region has a particular flow behavior and can be connected with other regions that flow in and out of each other, forming a graph structure. This is what's called constructing a Morse decomposition made by Qian et al. Finally, you can also discretize the edges of each triangle. The work by Bhatia et al. Introduces edge maps, which segment a triangle based on connecting inflow and outflow along its edges. This provides useful information for consistently following a flow. Next, I'd like to describe the discrete representation that we generate. I will explain how it's defined and used. A discrete vector field is based on Foreman's work in discrete Morse theory. The main takeaway for applying this work is that you need to choose which simplices to pair together. Each simplex, or component of the mesh, either a vertex, edge, or triangle, can be paired with only one other directly adjacent simplex. In 2D, that means you can pair a vertex with one of its edges, or an edge with either of its triangles. We like to think of the discrete vectors as flow between the centers of the paired simplices. The direction of this flow goes from lower to higher dimension, meaning you flow from vertex to edge or edge to triangle. The simplices that are not paired, we call discrete critical points, the discrete analog to the critical points I mentioned earlier. Now, the discrete analog for streamlines are V-paths. A V-path is a collection of adjacent pairs with the same type, which you can follow to form a particular path along the mesh. In this example, you can see that V-paths followed from this discrete saddle in white, where a discrete saddle is going to be an unpaired edge, and these lines form the discrete separatrices of this field. Now the question is, how do we choose these discrete vectors to make a discrete field that is similar to the original flow? And in order to do this, we look over to what they do in scalar field topology for inspiration. An algorithm by Robbins et al. Generates discrete vectors based on each vertex's lower star to make a discrete gradient field. First off, a star is defined as the entire neighborhood of simplices around a vertex, seen in the dark gray here. Then a lower star is a subset of those simplices which move toward a lower scalar value. In this example, you can see vertex 10 has the simplices associated with 876 because they're all lower than 10. Then the algorithm looks at each lower star and generates discrete vectors on the simplices in the lower star. The key is that each simplex will only belong to one vertex's lower star, meaning they can be processed independently. We've developed an outward star for vector fields. Intuitively, the outward star is the set of simplices around a vertex which have mostly outward flow. To determine the outward flow, first we look at the edges in the mesh. To calculate it, we use an equivalent version of the formula computed in FastCVT along an edge. To do this, we use the average vector along an edge, dotted with the edge direction, to determine the direction and strength of the flow along that edge. In this example, the blue vertex will have this edge in its outward star, because the flow direction moves away from it. Then we propagate this notion up to triangles by ensuring consistency with edges. So if 2 edges of a triangle belong to a vertex's outward star, we also add that triangle to the outward star. Note that this definition means that not all triangles are included in an outward star because they might have rotating flow behavior as seen here. So with the set of outward stars defined, we can now apply Robbins' algorithm with minor modifications to generate the discrete vectors for each outward star. Again, the key is that our definition ensures that a simplex can only belong to at most one outward star, with the triangle potentially belonging to no outward star, meaning that it would remain unpaired. Now that the discrete vectors are chosen, we have a set of discrete critical points and would like to determine which of these features are the most prominent by simplifying the field. To perform simplification, we use a saddle-based approach, where the v-paths are traced from the saddles, where again, a saddle is an unpaired edge in the field. Here's an example of two such paths. When we flip a path, the discrete vectors reverse their direction. When the path connects to another discrete critical point, flipping the path will remove both the saddle and the critical point from the field. The other option we consider is if the path reconnects to itself. We call this a saddle orbit connection. When we flip this path, the orbit is broken and the saddle is moved onto the orbit. We do this because it now allows all possible discrete critical points to be simplified, even those nested within orbits. Next, I'd like to highlight some results of our algorithm. We wanted to test our algorithm on handling a wide variety of vector field configurations and compare it to FastCVT. Thanks to an anonymous reviewer's suggestion, we did this by generating 1,000 random vector fields on a regular grid about 256 by 256 and smooth the field with Gaussian smoothing until about 200 critical points remained. This resulted in a total of about 201,000 piecewise linear critical points, as you can see by the dashed red line. On the left, we see both algorithms performed well in capturing the majority of critical points, with a discrete critical point generated nearby to capture it. The ones that weren't captured, we saw them to be unstable, meaning a little bit of perturbation would eliminate the PL critical point. On the right, the total number of discrete critical points generated by both algorithms was a little bit less than double the number of piecewise linear critical points. These were typically attributed to boundary artifacts or sharp curvature in the flow that couldn't be represented by the discrete vectors. And these results don't just apply to random vector fields. In one of our experiments with a smaller ocean flow dataset, we noticed this behavior with extra discrete critical points happening along sharply curved regions, with two examples shown here. After simplification to the number of piecewise linear critical points, these extra critical points were eliminated, showing the effectiveness of simplification. For other results, feel free to check out our paper. To conclude, our algorithm is fast and easy to parallelize because we based it on work in scalar field topology. Although we look locally, we still produce results similar to FastCVT. The algorithm was implemented using the topology toolkit and will soon be released in a future version. The discrete field offers advantages like robustness, but still has some limitations like generating the extra critical points like we saw. For future work, we would like to improve the outward star formula to account for curvature in the flow. We would also like to extend the algorithm to 3D and improve simplification through the use of an intuitive and fast compute interface. Thank you all for listening, and I'd be happy to take any questions.
All right, while people typing questions on Slido, I'm going to start with the first one. Would you mind go to the last page where you discuss the limitations, where you mentioned there's extra discrete critical points. I'm afraid I missed that. Would you please clarify further?
Yeah, so
where do they appear and why?
Yeah, so we compared to the piecewise linear evaluation on the vector field, and the red bar is going to be how many critical points are in the piecewise linear case. And then when we run our algorithm and FastCVT, they typically generate a little bit more critical points. So, and the reason for this is because typically on the data set we ran it on, there's a boundary. So it'll generate extra discrete critical points along the boundary because there's nothing for it to flow. There's no way to pair it along the boundary. And then for the underrepresented curvature, in this example, you can see how each of the triangles have a sharp kind of curvature. So the vectors go completely 180. So there's no way to, the triangle doesn't know where to pair its direction. So that's what results in these chains of critical points here.
So a follow-up question on Slido is that, can you resolve this issue with additional critical points in the examples by refining the grid in these areas?
From what we saw, no, because when we use piecewise linear interpolation and we subdivide the mesh, the curvature just gets smaller, but it's still sharp even within the individual triangles. So it'll still generate a chain of discrete critical points.
All right. Thank you very much. We're now going to move to our third speaker. This is going to be given by Mohamed. And he's going to talk about a practical solver for scalar data topological simplification. Please go ahead.
Hello, thanks for the introduction. Hey everyone. Topological data analysis is a class of technique for modeling structural pattern hidden in data. Among the most popular objects in TDA, the persistence diagram is particularly popular as it encodes the main feature in the dataset. In this example, the two purple bar encode the hills and the small blue encode the pits. In addition, this diagram is robust to noise, which makes it very useful in practice. However, in many applications, one would like to distinguish the features who can be considered as a signal from those who can be considered as a noise, and it is application dependent. In this context, we would like to be able to visualize a simplified version of the original data that admits the simplified diagram, and it is what our work is all about. So in the current state of art, topological simplification method are generally divided in two categories, combinatorial and numerical approach, each with distinct strengths and weakness. However, several methods are restricted to simplify the persistence pair that involve extrema, and this limitation become especially critical in three-dimensional scalar fields, where they are unable to address saddle pair, which are essential for more advanced simplification. Recent advances in persistence optimization have some potential, particularly with the use of the stochastic subgradient descent technique. We will call this technique the baseline approach. However, these methods have a long runtime for large datasets. So we have developed a practical solver for optimizing topological simplification that allowing the fast update of the persistence diagram and the pair assignment without the need for full recomputation at each step. There are several key applications: multi-scale data analysis, which reduce a visual clutter, and a surface genus repair, essential in the field like geometric modeling and geometric processing. Our implementation is open source and written in C++. So let's look together at the baseline algorithm. We start by inputting the scalar fields and the target diagram. The target diagram is created by copying the diagram of the input fields and then removing the pair which are considered as no signal, A in cyan. Next, we compute the persistence diagram of the current fields. This is based on an assignment problem, and this allows us to identify which pair we need to modify to make the scalar field persistence diagram more similar to the target diagram. Once the assignment is computed, we optimize our data to minimize the vast distance between the target diagram and the diagram of the current fields. And we repeat this step until the convergence is achieved. And then we return the optimized data where the undesirable features have been removed while maintaining the pair considered as a signal. We have observed that nearly all the execution time during each iteration is dedicated to computing the persistence diagram and the vast distance. Therefore, we focus on improving these two steps of the algorithm to make it run faster. Today, I will not describe the step involving the gradient descent, how to update the data, but it is documented in the section 4.1 of our paper. As we saw in the previous slide, we compute the persistence diagram of our data at each iteration. This leads us to consider how we could speed up this process. It is important to note that we use the DMS algorithm to compute the persistence diagram. Upon closer examination of the DMS algorithm, we found that 66% of the time is spent to compute the discrete gradient. Since the discrete gradient is a local operation, with each vertex having its own discrete gradient, we modify the algorithm to compute the discrete gradient only for the vertices that are modified in the previous iteration and the neighbors. For all the other, we reuse the discrete gradient from the previous iteration. This is significantly reduced the computation time while computing exactly the same diagram. The other step in the algorithm is the assignment optimization between the diagram of our data and the target diagram. We observe that certain pairs remain unchanged through the execution. That means they keep the same critical vertices in the data. Therefore, we can return their matching with the target diagram. In practice, for the simplification considered in our experiments, 84% of the pair remain unsensed, so we take advantage of that and only run the assignment for the remaining pair. We conduct our test on real datasets in both 2D and 3D, with the diagram containing over 3 million persistence pairs. The goal here was to simplify the pair with the persistence smaller than 1% of the function range. Our experiments demonstrate that we are able to simplify the dataset in just a few minutes, whereas it would have taken more than 24 hours to achieve the same with the baseline algorithm. We also demonstrate that this new method outperforms existing state-of-art framework, achieving 60 times faster on average performance. For the application, we address the challenge for extracting and visualizing the core structure of blood vessel from a complex scalar fields, accurate from the network arteries. Initially, the core structure is captured with the discrete integral line, here in green. However, the scalar fields induce many spurious loops in the filament structure, leading to inaccuracy in the vascular model. Saddle connector reversal, which is a classical technique, is inadequate in this scenario. It failed to eliminate the spurious loop without compromising the validity of the gradient. However, our approach generates a new function that approximates the initial data, optimizing saddle pair cancellation while returning the key data features. This simplifies the visualization by removing unweighted isosurface handles and spurious loop, improving the accuracy of the vascular structure. Another example in cosmology, where our method significantly reduced the visual clutter by decreasing the number of connected components and returning only the most persistent cycle. Our framework can also be used to repair genus defects in surface, either by cutting handles or by filling them. So, to conclude, we developed a practical solver for topological simplification of scalar data. The result is a method that is not only easy to implement, but also significantly faster, making topological simplification optimization practical for real-life datasets. The code is available on TTK. Our resource has been certified with the replicability step, and you can find all the application of this presentation online. So thank you for your attention. That concludes my presentation, and I'm happy to take any question you may have.
All right, thank you very much. I will ask my first question while other folks are typing on Slido. So my question is, when you mentioned the repairment for the genus, would you please go to that slide? Yes.
Yes.
So it seems to me that your repairment is filling it in, but not necessarily reconnect. Would you please clarify that a bit more?
So we can choose in our algorithm if we want to cut or filling the hills. And for that, we choose if you want, for example, to put cutting, you need to optimize only the bird gradients. Or if you want to fill the domain, you need to optimize the depth gradient.
So this is a very user-driven operation?
Yes.
Okay. All right. So far, I don't see any questions, additional questions on Slido. So I would encourage the discussion to carry on Discord.
Okay,
we will move on to the next speaker. Thank you very much.
Thank you.
All right, so our next speaker is going to be Tushar, who is going to talk about uncertainty visualization of critical points of 2D scalar fields for parametric and nonparametric probabilistic models. Please go ahead, Tushar.
Hi everyone, I'm Tushar Athawale, research scientist at Oak Ridge
Sorry,
National
Tushar.
Lab.
You
Yeah.
have to be in. You have to play your slides.
Yeah, I have
It's not
shared
a
my
full
screen.
screen at the moment.
I'm seeing artifacts. I think you should reshare the screen.
Should I reshare the screen? Okay. Let me reshare it. Is it looking better?
Yes, perfect.
All right. Hello everyone, I'm Tushar Athawale, research scientist at Oak Ridge National Lab, and today I will present our work on uncertainty visualization of critical points. This is the collaboration between Oak Ridge National Lab and Ski Institute, University of Utah. Now, critical point visualization is one of the fundamental techniques to understand the topology of complex scientific data with diverse application domains from climate science to biology. However, noise in the data can move or newly create critical points, thus leading to misinformation and possibly misleading scientific conclusions. Now, attaching error bars or probability bars to these critical points can help to mitigate this misinformation. And there has been some previous research that addressed this challenge. However, there are two limitations of the existing work. Most of the techniques resort to computationally expensive Monte Carlo sampling of underlying distributions, which are difficult to accommodate in visualization tools, and they assume restricted shape of these underlying distributions. So in this work, we address these limitations of existing work by deriving or proposing closed form solutions of critical point uncertainty, which are for both parametric and non-parametric models, which are way faster than Monte Carlo sampling. And additionally, we make them parallel with using VTKM library for GPU acceleration. We show up to 1646 times speedups compared to existing techniques, and which enables us to integrate our methods with visualization tools like ParaView. Now, there has been lots of research going on in uncertainty visualization field over past couple of decades, touching on various aspects from where different types of data and distribution models and so on and so forth, which really motivated us to study this problem. Now, critical points in deterministic or fixed data essentially represent points where gradient of the field vanishes. And there are three types of critical points, as we saw in earlier discussions. However, when we have uncertainty in the data, which is mostly the case for real-world data sets, we cannot deterministically classify if point is critical or not. So we ask this question, what is the probability of point being one of these types? And to simplify, I will just discuss our approach for a 1D case for computation of local minimum probability at point P. But these things my approach explanation extrapolates to 2D case as well as other types of critical points. So really the question we are asking is, what is the probability that x1 is simultaneously smaller than x2 and x3 in order for it to be local minimum? And it can be done through this triple integration on the top right, where we just integrate that joint distribution of three densities over the support where x1 is simultaneously smaller than x2 and x3. Now, but how to compute it in closed form and also in programmatically? So if you look closely, if you look at this red segment here, essentially this red segment is always greater than random variable x2, and hence it cannot ever result in local minimum. So we essentially do this compute this triple integral in a piecewise fashion. Then we look at this other piece in green, which is always smaller than x2 and x3, and hence this triple integral simplifies to this one integral because the inner integrals do not depend on value of x1 for this green segment. And similarly, we compute other two pieces. And if we look at holistically to this problem, there are only two observations that we made. So pieces depend on the start points of the intervals, which are a1, a2, a3, and this minimum of b1, b2, b3. And this triple integral simplifies to only four types of integration types, which we call integral templates. And computation of this, so what we do is we pre-compute these integral templates, which are at the heart of our algorithm. Now, thanks to Wolfram Alpha, because what we do is in order to compute expression for these integrals, we have to plug in uniform distribution or Ipanishnikov distribution, and deriving these integrals in a handwritten fashion is way too tedious and can take forever. So Wolfram Alpha really helped us to derive these long expressions. And then the algorithm essentially corresponds to sorting these start points and then to figure out the pieces, and then computing these integral templates on fly and summing them up. So that gives us the local minimum probability of x1 being smaller than x2 and x3. Now, the time complexity is order of n log n, where n is number of start points, and it's extremely efficient than Monte Carlo. Now, I just explained for 1D case, but for the 2D case, we have 5 integrals. So we solved that case in the paper. Now, for non-parametric noise, essentially for histograms, it's histograms, we again derive closed form solution, and we leveraged our closed form solution for uniform distribution. Histogram is nothing but a superposition of weighted and shifted uniforms. So you basically loop through all these uniform combinations and leverage the uniform distribution case I described earlier to derive local minimum probability. However, the downside is the time, although it gives more accurate UQ than parametric, it is computationally expensive because the time complexity grows exponentially with number of histogram bins. So we address that challenge too. We have proposed some semi-analytical solution, so combination of closed form and Monte Carlo, and we also implemented it with VTKM for GPU acceleration. Now to show you some results, first we confirm that our algorithms are indeed correct. So for that, we added a uniform noise to this Athawale function, synthetic Athawale function, to generate 50 ensemble members. And the left 2 columns shows the results of Monte Carlo sampling. Now you start, as we increase number of samples, the results start converging to our closed form solution, which is in the center column, C. Which is good, and our closed form solution provided 64 times speed up with compared to Monte Carlo sampling. Also, rightmost image shows the convergence curve. As you increase number of Monte Carlo samples, the distance between the closed form solution and Monte Carlo drops. So which confirms correctness of our algorithms. We tried similar experiment for saddle also, other types of critical point. Now, in second synthetic experiment, we wanted to test compare different probability models for uncertainty visualization of critical point. So we generated this ensemble member of 50 ensemble members, where 40 members corresponded to truth, where these 2 Gaussians are situated northwest, southeast. And then the noise we considered as a rotated version, a 90-degree rotated version, as 10 ensemble members. Now, if we'll start from the left column, uniform noise model, it is the fastest, but it shows that all 4 Gaussians are equally probable, which is not desirable result. We wanted northwest and southeast to be highlighted more. However, we move to Gaussian and Impedance-Nico, suddenly we start seeing that pattern, the desired pattern, where the noisy peaks are smeared out. Now, multivariate Gaussian was counterintuitive. It has been studied and proposed in multiple prior studies, but it showed all 4 peaks high probability because it took into account correlation between data and outliers. So it is sensitive to outliers too. Whereas non-parametric models did the best in terms of quality, they highlighted these 2 peaks, true peaks, and smeared out noisy peaks, but they are computationally too expensive. So we had to integrate it with VTKM or some parallel library. Now, here is some real data set. So for the climate, leftmost image shows critical points of the climate data representing the cyclone centers. And we compress this data by the factor of 16. Now, the column C shows the probabilistic result obtained with Monte Carlo, which takes about 5 seconds to compute the result. Whereas the rightmost image, our proposed one, the closed form solutions themselves give the speed up of 411. And then VTKM or parallel library gives further speed up of 4x, totaling to 1646 speed up. For this ensemble data set, we did not know the ground truth. Here, the right 2 images show the 2 ensemble members and their critical points in yellow. And the left 4 images shows critical point probabilities for different models, different distribution models. and probabilities are mapped to sphere glyphs. So if you see bigger sphere and red sphere, it means higher probability. Now, if you see compare all four models, if you look at just independent histogram, all four models, inside the white box, you see a critical point with high probability in all four models. So you can trust that there is a critical point there. Now, whereas for column D, which is our proposed independent histogram or non-parametric model, if you look inside green boxes, you see many critical points that are red and bigger spheres, which appear to be small probability in other three models. So, so that was interesting result. Here we don't know the ground truth. We implemented our algorithms showed how our VTKM implementations seamlessly integrate with ParaView for practical use and broader accessibility. So to conclude, we presented this closed form framework for much more accurate and efficient solutions compared to existing Monte Carlo techniques. We integrated our algorithms using VTKM library and showed near real-time computation of critical point uncertainty, and also showed integration with visualization tools. So in the future, we would like to study how these things, our study extends to more number of neighbors, currently considering only 4 neighbors, and 3D data and other topological visualizations based on critical points such as persistence diagram and contour trees. So yeah, thanks for your attention.
Thank you very much, Tushar. Tushar, your video is turned off. Is that intentional?
Oh, was it completely turned off full time? Oh,
But
I'm
that's
so
okay.
sorry.
We can now see it.
Okay.
There are 2 questions. The first one is, you assume that only a finite interval has non-zero values, and you assume that the values are independent at neighboring grid points. Is resulting error small?
Yeah, so you are asking that independent assumption, are you asking about independent assumption, data independent?
Yeah, there's 2 assumptions. You assume, number one, only a finite interval has non-zero value, and the second assumption is the values are independent at neighboring grid point.
Right.
Based on those assumptions, is the resulting error small?
Yeah, I mean, actually, the resulting error can be bigger, you know, because of the independent assumption. You are saying that neighborings are not independent, but if you consider and take into account correlation, the probabilities, the overestimation of probabilities can be avoided, as shown in the previous studies also. So actually, right now it results in overestimation of probabilities. The correlation problem is tough one in terms of finding closed form solution, and a finite interval assumption is also true, which is reasonable for real world data, but again finding those bounds, right, is critical. So depending, our results are sensitive to the bounds, right, that are derived at each boxes or grid point. Yeah.
All right, so second question is, how much work would it be to adapt your methods to 3D?
That's a good question. So in 3D we have, let's say, 7 integrals in total. So I tried that on Wolfram Alpha, and Wolfram Alpha couldn't handle it, you know. So you have to either do it on paper, which I don't know if someone is willing to do that, or we need better software to do that. But really that was the bottleneck. Otherwise I would have done it for 3D, you know. So yeah.
So just to clarify, is it true that the closed form do exist in 3D? It's just computationally, it's much harder?
Yeah, it does exist. These all extrapolate to 3D or more number of neighbors. It's just that computing those integrals was really tedious, you know. Even that five integration level, it led to a term which was like summation of 300 other terms. Yeah, right now software is not able to handle big integrations more than that. So
all right. Because there's no more questions. Thank you very much. Let's move on to the next speaker. So the next speaker will be Nicholas, who's going to talk about inclusion depth for contour ensembles. Please go ahead.
Yes. All right. Hello, everyone. My name is Nicholas, and I'm going to present our work on inclusion depth for contour ensembles, as just mentioned. But first, let's start seeing where can we find contour ensembles in the wild? So there are several scenarios where we can find contour ensembles. One of these is geographical data analysis, shape analysis, image segmentation, or also meteorological forecasting. In the case of the latter, we often find scalar fields with quantities such as pressure or temperature, and we can use an ISO value to extract contours. Now, the question that these cases raise is, once we have such contour ensembles, how do we analyze them? And the most straightforward way to do it is using a technique called spaghetti plots. And this consists on overlaying the contours, as you can see on the left of the screen, on the left side of the screen. Spaghetti plots are very easy to understand and to implement and permit analyzing global trends in the ensemble. The issue is that as the number of ensemble members grows, they become cluttered and analyzing them becomes quite complex. Simpler alternatives exist, and one of those is the contour box plot, which was presented before. The contour box plot permits analyzing ensembles of contours using statistical quantities in the ensemble, such as the confidence intervals, median, the mean, and also the outliers. The key ingredient to be able to compute a contour box plot are contour depths. Contour depths assign a depth value to each contour in the ensemble, which signifies how central this ensemble member is. Intuitively, the more centered the ensemble member is in the ensemble, the higher the depth. So in this example, the one with the yellow color attains the higher depth, while the contours in the periphery attain a lower depth value. As mentioned in this paper, we present a new notion of contour depth called inclusion depth, which has three defining characteristics. First, it is theoretically sound, drawing inspiration from functional half-region depth. Second, it is simple to understand and to implement because it leverages this very intuitive inside-outside relationship between contours. And third, it has a more favorable scaling compared to what was used until now to compute depths, which was contour band depth, presented jointly with the contour box plot visual idiom. How do we compute inclusion depth? So let's say we have an ensemble of 4 contours, and we want to compute the inclusion depth of contour number 3. So the first thing is to ask for every other contour in the ensemble whether C3 is contained in that contour or it contains the contour. In this case, we can see that in 2 of the cases, C3 is in the contour, while in the 2 other cases, C3 contains the contour. We tally these counts and normalize them by the number of contours in the ensemble to obtain the proportion of contours that are inside and those that are outside. Having these proportions, computing the depths boil down to getting the minimum between these 2 quantities, which in the case of C3 is 0.5. C3 is the contour that attains the highest depth, and this is intuitive, same as in the example before, because it is located towards the middle of the ensemble. Now, in the other side, we have C1, which will attain the lowest depth. And visually, that is because if we do the counting of inside-outside relationships, C1 contains every contour in the ensemble. Already here, we can see one of the defining characteristics of inclusion depth. It only requires n comparisons per contour, which yields a total complexity of n squared, which in contrast to the n cube of contour band depth is an order of magnitude faster. Now, you might be wondering, this guy comes here and shows us a perfect contour ensemble. This is not what we are going to see in practice. Okay, real-life contours are, you are correct, rather messy. And to be able to deal with this, we use the same algorithm, but define a softer notion of containment. instead of saying just 1 if it's inside, 0 if it's outside, and so on and so forth, we count both proportions, the amount of C1 that is inside of Cj and the amount of Cj that is inside of Ci. So to show you some examples, in this case, we have first that a bit of the blue contour is outside of the red one, and the relationship reverses in the second example. You can see how the proportions, the trend also reverses. When the two contours move away from each other, then the two fractions accordingly go down. With this softer notion of containment, we can compute scores that are meaningful for ensembles that have real-life behavior with overlapping and crossover. And we called the new inclusion depth version using this softer containment notion, epsilon inclusion depth. To prove the effectiveness of our method, we perform experiments with synthetic data. And the first thing we observe here is how the speedup is indeed significant with respect to the prior contour bandit. In the y-axis, we see the time, and in the x-axis, we vary the size of the ensemble. We try the two methods, CBD and ID, and for each method, we try the strict and the modify/epsilon version. The thing to note here is that big white gap, which shows how the n-squared performance surveyed quite faster than what was possible before. We also checked if the depth estimates that we obtain with inclusion depth are comparable to those with contour band depth, as if this is not the case, that would be problematic for analysis yielding different conclusions. We tried a number of datasets, and we recommend you go to the paper to check all of them. And basically, we computed for all of these different variations the depths using inclusion depth and contour band depth. What we observed is that both in the strict versions and in the epsilon/modified versions, the behavior of the depths was similar. And we further validate this by computing derived quantities like the robust mean and the median, which also match accordingly. We also perform a comparison on real data, which allows us to see the behavior of the methods in real conditions. We tried medical image segmentation ensembles and also meteorological forecasting. For the sake of time, I will focus on the former. So what you see here is an ensemble of more than 100 contours from a probabilistic neural network, which generates many hypotheses as to where an organ is in the CT scan, in this case, the parotid gland, of a head and neck cancer patient. As you can see, at this point, the spaghetti plot is quite complex with a lot of occlusions and clutter, making it quite difficult to see the particularities of the data. This is a perfect use case to use an idiom like the contour box plot, which of course we used. What we see here is the box plot computed with the depths from the contour band depth in the middle and from inclusion depth in the right. As you can see, visually the two are very similar. The only main difference is in the yellow line, which corresponds to the median, which is a very sensible derivative quantity, because even if the three same contours have the highest depths, one little change in order will change the contour that gets displayed. Besides this, we show very good agreement between the two methods, and strikingly, inclusion depth performs the analysis in 15 seconds, and contour band depth in more than 3,000 seconds. So to conclude, in this paper, we presented inclusion depth, a new notion of contour depth, which significantly accelerates previous methods without compromising quality of the depth estimates. This makes contour depth way more applicable in practice, and not only to compute contour box plots. Actually, depths can be used for other things, which we already showed early this year in EuroVis, where we applied the contour depth framework to detect different modes of variation in contour ensembles, which serves to create things like this multimodal contour box plot. But you can also use it in other contexts like regression and clustering. If you want to try contour depth in your own data, please check out our package contour depth by scanning the QR code right there. Thank you very much, and I am happy to take some questions.
All right, thank you. There's a first question on Slido. Am I correct that this technique assumes that all ensembles have exactly one contour? Or is there a way to generalize this to ensembles that might have 0 or n number of contours?
Yeah, so if I understand correctly, indeed, the method assumes that there are at least 2 contours in which you can check the inside-outside relationship. The edge cases where you have less than 2 contours, then you could include them in the code as we did in the library. In terms of more, sorry.
Just to clarify, I think
Yeah.
this question means each ensemble when you're computing this, each ensemble member provide exactly one contour.
Oh, so we are talking more, what if they are disconnected components?
Yes.
And in that case, our method generalizes directly to those cases, as we show in the paper, because we work directly with the rasters, using a notion of set depth, in which we compare 2 rasters instead, as opposed to, for example, a boundary loop representation of the contour.
To understand your answer correctly, is that if I have a particular ensemble member whose contour, or a few ensemble member which provide more than one contour at a fixed thing, this method still handles that situation.
Yeah, exactly. It will still handle it.
Okay. All right. Yep, I don't see additional questions on Slido. So let's move on to the next speaker. Please feel free to continue the discussion on Discord. Thank you very much.
Thank you.
All right, so our last speaker of the session is by Wang, who is going to talk about curve segment neighborhood-based vector field exploration. Please go ahead. And somehow, again, Wen's video is not showing, or is he showing? Just want to make sure. Okay, I think we're good. Please go ahead.
Hello, can you hear me?
Yes.
Can you hear me? Sorry.
Yes.
All right, so let me begin. Good morning, I'm Günther, a PhD student from the University of Houston. I'll be presenting our work on curve segment neighborhood-based vector field exploration. This research was conducted with my advisor, Dr. Qian. Our work addresses some key challenges in flow visualization, particularly in exploring and understanding complex vector field data. Flow visualization is a crucial tool in many scientific and engineering disciplines, helping us understand complex fluid dynamics and make important discoveries. However, as our simulations and data collection methods become more advanced, we face growing challenges in effectively analyzing and interpreting this wealth of information. Today, I'll discuss our approach to addressing some key challenges in the field. Firstly, visual clutter is a major challenge in large-scale curve visualization. When rendering numerous curves, important patterns and structures can become hidden, making interpretation difficult. Secondly, the volume of data in large-scale curve dataset presents significant computational challenges, affecting real-time processing and interaction crucial for effective exploration. Thirdly, identifying meaningful features in complex datasets is not straightforward. Current methods often rely on user-specified references or parameters, which can be limiting or biased. Lastly, many existing analysis techniques don't scale well to large dataset. This limitation becomes apparent when applying current clustering and pattern search methods to extensive curve data. These challenges underscore the need for new approaches that can handle the scale and complexity of modern curve-based datasets, while providing intuitive and interactive exploration tools. Our work addresses the challenges in flow visualization through several key contributions. Firstly, we introduced the curve segment neighborhood graph, a novel representation that captures the spatial relationships between curve segments in flow data. To tackle the challenge of efficiently analyzing large-scale datasets, we employ community detection algorithms, particularly the Levine method, We choose this approach for several reasons. Firstly is that the Levine method is known for its efficiency and scalability, making it suitable for large-scale flow data. Secondly, it produces a hierarchical community structure, aligning well with our multi-layered visualization approach. Thirdly, the method tends to find a good balance between the number of communities and their sizes, which is crucial for meaningful pattern analysis in flow data. We develop a multi-layered Vortex layout for the resulting communities. This visualization technique helps review the structure and patterns within the flow data at multiple scales. And by combining these features, our framework provides a powerful toolset for exploring and understanding complex flow structure, addressing the challenges of visual clutter, computational complexity, feature identification, and scalability in large-scale curve-based dataset. Let's go over the pipeline of our framework. First, we start by loading a streamlined dataset and decomposing the curves into smaller segments. This gives us a set of discrete elements to work with. Next, we construct the CSNG graph, which represent the relationships between neighboring curve segments. We use either k-nearest neighbors or radius-based neighbors to determine which segments are connected in the graph. Next, once we have constructed the CSNG, we apply community detection algorithms to identify clusters of similar segments. This step automatically groups segments that are closely related, potentially corresponding to meaningful flow features or patterns. Finally, we provide an interactive tool for users to refine the result. This includes the ability to merge or split communities, allowing experts to incorporate the domain knowledge to fix any misclassification from the automatic process. This step ensures the final groupings accurately represent the important structure in the flow. And also, this is a web-based framework, which means that it can run in any device with a modern browser, ensuring maximum accessibility. Our user interface consists of two main panels that work together to provide a comprehensive view of the flow data. On the left side, we have a 3D visualization panel. This shows the actual streamlines and segments in three-dimensional space. When user selects communities in the graph view, the corresponding segments are highlighted in the 3D view. On the right side, we have force-directed graph view, which shows an abstract representation of our data, where each node represents a community of curve segments. The size of each node indicates how many segments are in that community, and users can interact with the graph, selecting, merging, or splitting communities as needed. This allows for intuitive exploration of the data structure. Together, these panels allow users to smoothly transition between high-level structure and the detailed examination of specific flow structures. Let's walk through an exploration of the Plume dataset using our tool. We first obtain community detection result from performing neighbor search, which k equals to 60 and Levine resolution 1. In the first step, we see the full Plume visualization in 3D, which colors representing different communities detected by the Levine algorithm. This gives us an initial overview of the flow structure with about a dozen distinct communities visible. The corresponding graph view shows how these communities are related to each other in our abstract representation. Moving on to the second step, we've identified a community of particular interest, highlighted in blue. This community stands out because it contains many interesting vortex-like features from the middle and the end part of the Plume dataset. Notice how the selection is reflected in both the 3D view and the graph view. Next, we've taken that large community of interest and split it into smaller subcommunities. This reviews more detailed structure within the area that we identified as interesting. The graph view now shows a hierarchical structure. The original large community is now represented by a bubble containing new, smaller communities. This visual metaphor helps us maintain context while exploring finer details. Moving on, we've identified 5 subcommunities of particular interest, numbered 14, 15, 20, 23, and 24. Communities 15 and 20 together form an interesting vortex feature. This feature appears to be split between 2 communities, suggesting a complex structure that wasn't immediately apparent in our initial view. Similarly, 14, 23, and 24 together form 2 more interesting vortex features. This level of details allows us to precisely pinpoint and analyze specific flow structure within our larger area of interest. By iteratively refining our view like this, we can uncover intricate flow patterns that might be missed in a more general analysis. So we merge communities 15 and 20 together and separately combine 14, 23, and 24, unifying the previously split vortex features. This change is reflected in both the 3D and the graph view, showing the structure as cohesive entities. Our tool's flexibility allows us to navigate between different levels of detail, starting broad, refining to review detailed structure, and then recombining elements to highlight key features. This iterative process of splitting and merging enables us to arrive at a representation that best captures the important aspects of the flow. Through this exploration, we've gained significant insights into the plume structure, identifying and isolating key vortex features that might have been difficult to discern initially. Let's briefly review the two methods we're using for comparison and why this comparison is important. To recap, Levine is a graph-based algorithm that automatically detects communities and reviews hierarchical relationship in the data. It's particularly well-suited for our CSNG representation due to its efficiency and ability to work directly on graph structure. For comparison, we're also looking at PCA k-means, which combines dimensionality reduction with traditional k-means clustering. Comparing these methods is important because it helps us understand the strengths and limitations of our CSNG approach. Our comparison of Levine and PCA k-means on the plume dataset reviews distinct approach to community detection. So in the 3D rendering, our method shows slightly better coherence in identifying vortex-like structure, while the post-directed layouts can highlight the complex internet-connected community structure. And for PCA k-means, it's a lot faster, but it tends to produce more this disconnected cluster. So you can see here, because there's no neighbor search, right? So these initial observations, while insightful, requires further comprehensive evaluation across various datasets for better conclusions. So in conclusion, our work introduces the curve segment neighborhood graph as a novel approach to represent relationships between curve segments in flow visualization. We've adapted community detection algorithms for efficient segment clustering and developed a multi-layered four-directed layout for interactive exploration, including a web-based accessible web application. Our method has shown effectiveness in exploring complex 3D patterns across several different streamlined datasets. In future work, we plan to study the impact of different neighbor search methods on CSNG construction and conduct a comprehensive evaluation, including comparison with existing techniques and user studies. These efforts will help refine and validate our method, enhancing its utility in flow visualization. Thank you. Question?
All right, thank you very much. There's one question. Is the CSNG stable with respect to how a curve is defined? Do you consider the maximal streamlines as a curve as compared to a segment of the streamline?
That's a very good question. We are quite flexible in defining what each individual node in the CSNG graph represent. In our case, currently we're defining as a single segment. Now, this segment can change depending on your streamline decomposition strategy. So we can either just decompose the streamline as it is, so each segment represent one segment within the CSNG graph, or there are several strategies on how to decompose a streamline more intelligently, which breaks down the streamline at more based on the behavior of the streamline instead. So there are several other related works on streamline decomposition also.
Right, just to clarify a bit more, is that if you choose a different representation, slightly define a different type of curve, is your CSNG produce similar result?
Technically, CSNG is designed to work with any curve-based data. So my answer would be yes.
Even if I take a curve and then divide it by, say, 10 segment versus divided by 20 segment, is the results going to not change too much?
So the resulting CSNG itself is only a graph representation, right? The actual CSNG is produced from performing KNN or RBN neighbor search on the resulting curve-based data. So I apologize, it will change based on how you decompose the streamline and based on the parameters you set for the neighbor search methods.
All right. Okay, I see there's a warning that our room is going to close very soon. So I would like to thank all the speakers for this session, as well as the student volunteers. Thank you very much. Please continue your discussion on Discord and enjoy the last day of this. All right.